will be a revision and solving some exercises for simple harmonic motion, a very essential concept in, well, classical mechanics. So, firstly, what is simple harmonic motion? So this is a periodic motion. It is a periodic motion where the restoring force is directly proportional to the displacement. I guess it's like x or y. And opposite in direction. So we could see, for instance, that one of the most important equations that we are going to use, and we're going to talk about this one a bit later, but just to talk about it now, F is equal to negative kx. So this equation will be the most essential, or at least one of the most essential, in simple harmonic motion, which we will talk about a bit later. So in simple harmonic motion, you must always have a stable equilibrium position. Anytime you displace something in the system, it must feel a restoring force, because restoring force is directly proportional to the displacement. The restoring force is linear in displacement. The motion must be periodic, and energy oscillates between kinetic and potential. And so we are going to explore these key properties and these fundamental things about simple harmonic motion. So firstly, we can see that from Newton's second law, which is F is equal to ma, this is Newton's second law, which will be very important to us, just like F is equal to negative kx. We see that we could substitute this as a restoring force. So ma will be equal to negative kx. And so that means that we could rewrite that acceleration will be negative k over mx. And so we could see that a can be written as the double derivative of x, right? So this is the derivative of speed dt, or better yet, you could write it as the double derivative of x plus omega squared, which is the angular frequency x, is equal to 0. So essentially what we did is that this k over m is omega. Omega is equal to the square root of k over m. So not this, but the square root of k over m is the angular frequency. It is the angular velocity of a simple harmonic motion system, specifically, which this will help us a lot about specifically spring mass systems, not just any ordinary simple harmonic motion, but specifically spring mass systems will help us with this. And so we could see that the acceleration of the system is directly proportional to the square of the angular frequency. So let's start talking about the mass spring system, in which we will use the especially this equation and F is equal to ma. So of course F is equal to negative kx will be the most important equation, because this is Hooke's law, and Hooke's law is the law of the springs. So when you'll have, for instance, you can have something like this, a wall, and then you have a spring attached to a mass, and let's say this mass is at equilibrium. So it is at x is equal to 0. This is A. And so when you are going to displace this mass from equilibrium, let's say here, or no, maybe let's put it right over here. The mass is now here. X equals 0. You have displaced it of x. And now, because it was displaced, it feels a restoring force in the direction opposite of the displacement. And so when you let go, it will pass for a while. It will pass in here at equilibrium. It will not stay here. In fact, this is where its velocity will be max. It will have max velocity, but the restoring force will equal to 0 because acceleration will be equal to 0. So this is just for a while, just for this is B, this is C, and this is temporary. And then it will come here where it is at negative x from the from equilibrium, and of course it will feel a restoring force in the opposite direction to try to bring to equilibrium, because the mass wants to be at equilibrium. That's what the mass wants. Reality tries to really pull it to the center, pull it back to equilibrium, and so when you displace it, it will feel a restoring force, which is Hooke's law, to try to put it back in the center. So Hooke's law is of course essential here because this is how springs work. Normally you learn that springs operate through Hooke's law, with x being the displacement and k representing the constant of the stiffness of the spring. So we could derive essentially the motion for mass springs specifically, not just a graph, but let's mathematically. So firstly, like we did before, right? Ma or md squared x dt. So the double derivative of displacement is acceleration. So ma, which is Newton's second law, is equal to the restoring force, Hooke's law. So both of these, it's equal, and this is Hooke's law. And so we are going to divide by m, and again get that the angular frequency is a square root of k over m. This is exactly what we did before here, essentially. Exactly what we have here. It is the same thing for the mass spring system. This is how you get it for a mass spring system. So essentially, what we did here, the equations we did, and the equivalence between Newton's second law and this Hooke's law is specifically for mass spring system, not any ordinary simple harmonic motion, but you could use this only for a mass spring system. And we have the same thing. We could derive it again, and we could see that acceleration will be equal to negative k over mx, or we could write it as a is equal to negative angular frequency squared x. So we could write it just like we did before, and so we could get it to the final form with xt, a function of displacement to see what the motion is equal to the amplitude times cos times the phase. And the phase is this. This describes essentially the angle at which it will be, which will follow a sort of circular path, because this is called the phase. We already know this, which is the angular frequency, the angular velocity, and this is a constant. This is the phase constant that describes the phase of the system, and this one equation describes essentially motion. To derive motion for a mass spring system. And so from these equations that we got essentially before here, which we talked about around here, that of the restoring force of Newton's second law and how it's equivalent to the restoring force, which here would be Hooke's law, how we already derived angular frequency here, which is the equivalent here at the mass spring system. We could see that it moves when you have a periodic motion that keeps moving and moving, because this will move again and again, right? It will try to be at equilibrium, but then it will go, and then it'll have a force trying to pull it to equilibrium, and then it will move more here, and then it'll try to pull it equilibrium. So it's very periodic, and so the motion of this periodic motion, of this simple harmonic motion, will be explained through this equation, which the amplitude will specifically be the maximum displacement, which so in this equation it will be maximum displacement, but in a graph it will be the amplitude of the wave, because if you are to graph this in time and displacement, which here would be x, you would see something like this. You'll have a sinusoidal motion because it is periodic motion, so you will have a wave-like function. With this is the amplitude, this will be the amplitude, and of course you'll have periods. This will be t over 2, you'll have t, and so on and so forth. Or no, maybe I'm just gonna maybe here we will have t over 2, and then you'll have here t over 3 and t over 4, and the t will be the period, which is the time it takes to do one cycle. And so maybe a cycle could be this could be a cycle, and so this will take some time to take a cycle, and so on and so forth. That it would be the period of the system, which the period we can describe, the period of, you could have an equation for this, which will be 2 pi over the angular frequency. And you could also have the frequency, which is the angular frequency over 2 pi. This you get because the period is 1 over f, 1 over frequency, because the period says the time it takes to do a cycle, and the frequency says how many cycles you get in a given amount of time. And this will be your initial condition. Your initial condition is this, is the phase constant. We could also derive velocity here. So our velocity, to derive velocity here, we can get negative a angular frequency times angular frequency sine of the phase acceleration. We could also derive acceleration, which will be negative a times angular frequency squared times cos of the phase. So as you can see, as you grow, it kind of changes, right? So to derive displacement here, to derive the equation of motion, we'll start with cos, and then you'll have sine, and then you'll have cos. This is, you could see the pattern here, which this mainly arises due to differential equations. And if you do some certain differential equations, you could see the pattern emerging, and to derive the velocity and acceleration of the system, you would need to use differential equations, which I will not use here. Now to do the energy, so the total mechanical energy in a system will be E is equal to 1 over 2 Ka squared, whereas the potential energy will be 1 over 2 Kx squared. So A, don't forget, is the amplitude of the wave. As you can see here, it's the amplitude. But you could also use it in this equation as the maximum displacement. So that's why it is the total mechanical energy. This is a potential energy. And the kinetic energy, well, it's like always, right? You always get mv squared. And energy will always just slosh back and forth, right? It will always go back and forth. Energy in a simple harmonic motion will be periodic, right? If we have a spring mass right here, and then you displace it here, it will, and then it will move all the way here. Let's put it here. It has gained kinetic energy and it has lost potential energy, right? But when it was here, it had more potential energy. So here, its potential energy was bigger and its kinetic energy was smaller. Here, its potential energy was lower and its kinetic energy was higher, for an example. And so we'll come back all the way here, and so on and so forth. So it changes a little bit, back and forth. Energy will be back and forth. Now this was for a mass spring. These equations for energy the wave, well, the waves can be, but for instance, this angular frequency, for instance, K, you won't have necessarily this restoring force has Hooke's law in a simple pendulum. This is mainly for mass spring systems. So if we go now to a simple pendulum as a simple harmonic motion, let's analyze this specific motion. So it consists always of a point mass m, a string length of L, and a gravitational field of G. So it will look something like this. It will be around here, and this is its this will be the equilibrium. You'll have a mass here, and notice that when it will vary, it will slosh like this. It will change like this. This is how it moves. Notice how different it is from mass spring systems, in which the periodic motion is linear. It was always linear. If we go back here, we could see that its displacement was on the x-axis, or you could have it on the y-axis. But this displacement was linear. Here you have angular displacement, which will be very important to see. And so here, the force that we'll have here, firstly, it will have a gravitational force. You could do you could simply do the forces on this, the free body diagram. This will be of length L. It will have a gravitational G, so this will be mg. It will have an angle there. This will be a point as m. And so for this angle, we could also decompose fg like this, and then we could see that this will be fg sine of theta, and this will be fg cos of theta. So using basic trigonometry, this theta is the same as this theta, and you could decompose this force using the angle, and you could see using trigonometry. So that means that our restoring force here will be the one. Always remember that the restoring force is a force trying to bring it back to the center, trying to bring it back to equilibrium. That is the goal of the restoring force. And the restoring force here, we could see that is this one right here, because it is trying to bring it back to the center. So as we can see, we will no longer have K or something like that. No longer will have the constant K for the stiffness of the spring, because we have no spring here. We have another fundamentally different restoring force. So that means the arc length will be the length of the arc will be L theta. So we'll use this as our x as our displacement, or not our displacement, but as our x. And the restoring force will be negative mg sine theta. Notice that it'll always be negative. Always will have negative because it is trying to oppose displacement. It's trying to bring it back to equilibrium. So we will have a negative force multiple times, just like here, and just like the first, just like with the spring mass system where we had negative kx. So we can derive the pendulum simple harmonic motion. So we could start, for instance, just like we did before. We have to, but here's the difference. Here we will work with angular things, right? We will work with angular displacement. So we'll try to do very similar to what we did to the spring mass simple harmonic motion to derive displacement and all of that, but we'll do it in the rotational analogs. So we'll have torque, which is the rotational analog of force, which we will use, which will be equal to negative mg times L sine of theta, right? Because L theta is our x, and mg will be our force. So, right, so it makes sense because if you remember, torque is equal to Fr sine of theta, and so we have our r, we have our mass, and we have our sine of theta. So this will be our torque, and this will be very important to us because what we did, as I said, what we did last time to derive motion, we have to firstly convert everything in rotational analog and then do it. So we have our force in rotational analog, which is torque. We need our mass in rotational analog, which is the moment of inertia. A system like this, which is basically like a ring, so it's like this, and it's not like a full sphere, which has a different moment of inertia. So we're talking about ring hoops type of moment of inertia, and that will be with the equation ml squared. And so we can do Newton's law just like we did before, but in rotational version. So torque is equal to I times angular acceleration. And so we're just going to substitute. So we'll have, we will have negative mg times L theta, which is our torque, which is equal to ml squared with an angular acceleration, just like we did before. Acceleration, we could write it as a double derivative of displacement, of the linear displacement. But here we have angular displacement, so we can write this as the secondary derivative of angular displacement. And so we can simplify a lot of things here. For instance, we can just we could divide by mass, and then we'll have negative g L theta, which is equal to L squared times d squared theta over dt squared. And then we could divide by L here. And so we'll have negative g over L theta, which is equal to d squared theta over dt squared. There we go. And so we will have now, by simplifying this, we could move this on the other side, and then we could write it d squared, the angular acceleration, plus g over L theta is equal to 0. And so we could see here that basically k over m has been replaced by g over L. So our angular frequency is now the square root of g over L. So for a pendulum, this is the angular frequency. So we could find a solution for pendulums, which is very similar to what we did before, except that here we don't have A. A was basically x max. So here we'll have theta max, which is its rotational analog, times cos of the phase. And so we could find the period is basically very similar to what we did before. Almost exactly the same. It's just that instead of K and M, we'll have L and G. We could find the potential energy. So we could find potential energy, which again, you have to take inspiration to what we did with spring masses, because spring masses will be almost identically imported to pendulum simple harmonic motion. But here we'll have U is equal to mgl 1 minus cos theta. For small, but this is in general, this is potential energy in general. If you want for small angles, you could approximate it to be 1/2 mgl theta squared, and its kinetic energy will be 1/2 of m L and the first derivative of, which is speed basically, which is angular velocity squared. So this is basically all there is need to know about simple harmonic motion. We could see what the period is here. The period, which is the time to take a cycle. We could see the amplitude of the waves, which this, just like you did before, just like you saw waves in the unit circle, you could also see the phase circle to understand what's going on. We talked about how to derive multiple equations of motions, velocity, acceleration, energy, and a couple graphs here of the simple harmonic motion of mass spring system and the pendulum. So now let's try to solve a problem. So a kid weighs 20 kilograms. The kid who weighs 20 kilograms swings on a 4-meter long rope. So already we can be sure that this is a pendulum problem. So we'll have to use the pendulum solutions in our toolbox. So we know we already have the mass, which is 20 kilograms. So we could see this. Let's say the child, we could write him as a circle, like a big old circle, and his mass would be 20 kilograms. And this is 4 meters, so L will be 4 meters. And the kid passes the lowest point with 6 meters per second. So the lowest point will be maybe around here. So the questions we have, is, what acceleration does she experience? What acceleration does she experience at the lowest point? So we could see that we are given the mass 20 kilograms, the length, we are given the speed at the bottom, and we already know that g is equal to 9.8 meters per second squared. And we could see that centripetal acceleration when moving into a circle. We could also find the centripetal acceleration, which is v squared over r. This is the equation for centripetal acceleration, which we will use to find multiple things. And so here it will be, and so here r is literally L, which is 4 meters. So we'll have 6 squared over 4, which is 36 over 4. And that will be, yeah. And we will get 9 meters per second squared. Which is very close to g. And so the radial force balance along the rope direction, we can know what the radial force is. The radial force will be equal to m times v squared over L, which is pretty self-explanatory. It would just be 20 times 9, right? 20, so which is 180 newtons. That'll be our radial force. And energy conservation, if we ignore air drag and friction, we'll have K plus U, which is equal to constant. So we want to know what the acceleration at the lowest point is, because that was our first question that was asked to us, and we used these, we found these, we try to organize everything we have to do, and we found this as our angular centrifuge. And so in reality, the acceleration at the lowest point is literally the centripetal acceleration, just like we solved it here. Now, our second question will be that how much tension is in the rope at that point. So once it at its lowest, and where essentially at the lowest point where the acceleration is 9 meters per second and the speed is 6 meters per second. No, the acceleration is 9 meters per second squared and speed or velocity is 6 meters per second. What is the tension in the rope? And so this was part A. This was our first problem solved, because acceleration AC will be equal to A at lowest point. And now for B. The tension in the rope at the lowest point. So we could draw the forces. So at the lowest point, it will look something like, you have a tension here and gravitational force. So we could use the radial. We could use Newton's second law, the radial one, which will be the net radial force will be the tension minus mg will be equal to mv squared over L, which we found it here at 180 newtons. This is very important to us. So because it feels an acceleration of 9 meters per second at its the centrifugal acceleration at its lowest point, it feels that it will have a force, a radial force here. And so the tension minus the mass, which we said is 20 kilograms, 20 times 9.8 is equal to 20 times, oh no, we already found it, it's 180. And so we'll just multiply 9.8 with 20 and add it with 180. And so, right, because we're going to put this like that. And so the tension will be equal to 180 plus 20 times 9.8. And this should give us 376 newtons. So this will be the tension that the rope will feel when the mass is at its lowest. So make no mistake, because you can do some mistakes in this problem. This might be a bit tricky. If you just take Newton's second law, if you could just take, I can just take Newton's second law, right? Here, because I could see that there's two forces, tension and Fg, so tension must be equal to mg, right? Well, this is wrong. Don't do this, because you have the radial force that you must take in consideration because of the centrifugal acceleration. Now, our next problem our next number for this problem will be, what is the maximum height that this mass can reach, or this child, because this child is on a swing. And so we found out that this child feels 376 newtons of force when he's at the bottom. And we also learned what's his acceleration when he's at the bottom, right? When he's very close to the ground on his little swing. So our equations right now were to see what happens when he's close to the ground, what happens when he's very close, when he's at his lowest point. Now we're doing the opposite. We want to see what is the maximum height that he can reach. And so we will use here energy, right? Because we're talking about height here, and so we're going to need to introduce things about potential energy, which does include height and kinetic energy. So here, basically what you can do is that it's so just like we did before, we found this k plus u is equal to constant. So basically we could just say that at the bottom, maximum speed, so will be maximum kinetic energy. But at the highest point, speed becomes 0 momentarily, so kinetic energy becomes 0, and all energy becomes gravitational potential. So that means that you'll have its kinetic energy will be equal to its potential energy. So because we want to have u initial, u when it's at the when the kid's at the bottom, plus k when he's at the bottom, will be equal to u when he's high, plus k when he's high. And these will cancel out, which is pretty trivial, I would say, which is pretty self-evident. Because he stops, because his kinetic energy will be 0 at the top, because he's reached his maximum point, so it's right before he falls, and of course he won't really have potential energy when he's at the bottom. So we'll have this equation that we'll use, which arises because energy is constant. And so we could cancel m here pretty easily. So we'll have v squared over 2, which is equal to gh. We just want to know h, which is pretty trivial problem, I would say. Which the v we already found that basically it's 6, so it'll be 6 squared over 2, which is equal to 9.8 h. So it'll just be 36 over 2 times 1 over 9.8, which would be equal to h. And so the highest point the kid will reach will be 1.8367 meters. So this will be the highest height that the kid will reach. All right, next problem will be, what is the acceleration at the highest rope, and what is the rope tension there? So this one, D, will actually be separated into 2 points, 2 problems, because we want to know the acceleration at the highest point and the rope tension. So we know that at the highest point, V will be equal to 0, hence why the kinetic energy was 0 at the last problem. And so therefore we can know that angular acceleration will be 0. However, we will still have gravity here. Gravity still acts, and it has a component along the arc. So let's firstly try to find the acceleration at the highest point. Even though, as we said before, even though centrifugal acceleration is 0, the gravitational acceleration is not 0. It's still 9.8. So we could split gravity into components. So we can make a graph here. So when he's at the highest point, let's say here, he'll feel gravity like this. But at angle theta, there'll be a radial component of mg cos theta, which is along the rope. So mg cos theta will be along the rope. And mg sin theta will be across the arc. This is mainly due to this angle right here. Just like we did before. Just like when we explained and we explored pendulum simple harmonic motion, we explained how theta here is the same as theta there. So tangential acceleration here, so even though we don't have centrifugal acceleration, we have tangential acceleration, which is g sin theta, which will be this one. So just remember, when you have motion in a circle, when a mass is moving across a circle, it could have tangential acceleration, which is this one right here. But it could also have centrifugal acceleration. Just to get this back, this is essential in rotational mechanics, and in classical mechanics in general. And here we see that our centrifugal acceleration has canceled, but we do have a tangential acceleration. So just to visualize what is going on, and we could see that because mg sin theta is across the arc, that g sin theta will be our tangential acceleration, because it's across the arc, across a circle, if you will. And so we can compute sin theta. So we do have cos theta. Cos theta is 0.5408. This number, cos theta, we have it. It's 0.5408. And so we can find sin of theta through the basic trigonometric equations by sin theta. Sin of theta will be equal to the square root of 1 minus cos squared. With this, of course, it's the trig identity, right? This is basic trigonometry. Sin squared plus cos squared is equal to 1. The basic trigonometric identity, the most essential one. And so sin theta, sin, will be equal to 1 square root of 1 minus 0.5408 squared. And so we will get, and so doing this calculation, we'll get sin theta as 0.841. And so the top acceleration, which will be equal to the tangential acceleration, will be g times sin of theta, which will be 9.8 times 0.841, which is equal to 8.24 meters per second. So it accelerates here. Its acceleration will be 8.24 meters per second. We could compare this to here. When its acceleration, we could see it here. It had 9 meters per second, so it's significantly slower than it was when I was at the bottom. Here we could see that it's 8.24 meters per second. Its tangential acceleration when I was at the top. But we are not done with this problem because we also want to know the tension at the highest point. Here again, we'll use the same equation as we did before, but as we can see, so just like we did before, T minus mg will be equal to the centrifugal Newton's second law, but ma, but the a is, or no, but the a is acceleration right here. This cancels out because this is 0. So in this case, you could use T is equal to mg. Before, you could not have used that. If you use that, it will be wrong. But here you can use it because speed is equal to 0. So you have to see if speed is equal to 0, if velocity is equal to 0, to see if you can apply this. And so you could easily know that the tension of the rope will just be 20 kilograms times 9.8, which is 105 newtons. But actually, no, it's not 105 newtons because you do have to multiply by cos theta. So here I did a mistake. Here's cos theta is equal to mv squared over L, which this cancels out. So you do have to multiply by 0.5408, and this will give 105 newtons. So I forgot this. This is pretty important to have the cos theta. But essentially this exercise I was trying to show you that just like the same before, but here you can use, is equal to 0 because here speed is equal to 0. That's about it, guys. Thank you.